the title of my first quarter research, and it's going to be my first year research anyway, is trade-off between heat production and heat intake in the rat. I'm sure the title's not clear, but it's going to be soon, as soon as I explain to you why I conducted this experiment. Okay? I'd like to start with an everyday experience of all of you. Let's say it's really cold outside. It's almost, anyway, but let's say it's about 40 degrees, okay? And I ask you, would you go outside with shorts and a t-shirt and try to remain warm by shivering? Or would you just put a coat, a heavy coat, and go outside? Well, before you ask the first, that you would go with a short, let me say you would go with a heavy coat, I'm sure. And let's say more, that you don't have this coat, you don't have heavy clothes at all. I'm sure if you rent the car, you would turn on the heater, okay? So, you would not shiver, but do some kind of behavior to keep your body warm. Well, scientists who study temperature regulation, body temperature regulation, have known for a long time that non-human animals do more or less the same. So, if they can use some kind of behavior, they would not use what's called autonomic responses, shivering in the cold or sweating in the heat or things like that. Now to these names in the title. Heat intake. By heat intake, I'm going to call this behavioral, for instance, turning on the heat, the heater in your car. You're going to get heat from the environment, so I'm calling it heat intake. And heat production, shivering. You're shivering, you're increasing your metabolism, producing heat. So, heat production. Well, there was for a long time this principle of primacy of behavior over autonomic responses. But it has been recently, let's say the last 10 years, shown that it's not exactly like that. Okay? It depends on the conditions for the behavioral response. Well, I have an example here, good, in humans again, okay? I'll say you will shiver a little in your bed at night instead of walking all the way to the closet to get another blanket, okay? So behavior is not so, it's not the king or the queen of temperature regulation, okay, the responses. Now, I think we have all the elements to go on. So, in this experiment, I showed this relativity of the behavior primacy in the rat. Okay, it has been shown for just a couple of other animals, but not for the rat, which is the most famous, the most used animal in research. So it had to be shown. Okay. One person that has been working on that subject with pigeons is Ingrid Schmidt, Dr. Ingrid Schmidt, who's visiting the department. Well, okay. So in my experiment, I had let's just have a short report of the apparatus, okay? It was just a plastic chamber, more or less cylindrical. Something, well, just a dome, whatever. Okay, and the rat is here. This is sealed because, and there's two. Let's put this way, because as I told you, I'm gonna, instead of measuring shiver, that's hard. You have to put an electrode in the rat and all this stuff. You measure oxygen consumption, because you know that you need oxygen to burn your whatever you eat and produce heat. So I measure oxygen with an equipment that was built to do that. Okay, I just put air in here and take this air out and goes to my equipment. And the red is here, and there's a bar, and the red presses the bar. When the red presses the bar, oh, this is cold, okay? It's 5 Celsius. 40, something about 40. Okay, 2 heat lamps, one on that side and one another here. Well, let's draw it here, but actually it's not here. It's to the other side. Okay, when the red presses the bar, it turns on the heat lamps for, let's say, 3 seconds, 10 seconds, and then turns off. It has to press the bar again to get another touch of heat. Okay, these are the variables. Okay, and I can change ambient temperature, I can change intensity of the reward, I can change the duration of the reward, and I can also change the force the rat has to, well, the force, the effort necessary to depress the lever. Okay? I'm not gonna go into details of the procedure because as soon as we see the results, the procedure will be really obvious. Okay, let's start with this one. The copy is not really good, but anyway, I'm gonna go to the other side. Okay, and this axis you have heat, okay, and this is the reward duration. So I'm changing. What I'm doing now is I change reward duration, only 2 values to make it simple, okay, from 3 seconds to 9 seconds, and I measure heat. Heat, either heat production, measured based on the oxygen consumption measurements, or heat intake based on the lamp. The time the lamp was on with all the corrections necessary. Okay? Well, what happens? If let's go this way. If I decrease reward duration, I'm decreasing the ability, the behavior efficacy, so heat intake will go down. Okay, I have less heat in each reward, so I get less heat at the end of the session. Well, when this happens, heat production, so heat intake went down, and wait here. Okay, and heat production went up. Of course, that's what should happen. Okay, sorry for that. So there's always there's in this case this trade-off. When heat intake goes down, heat production goes up. If you want to read now in the right side, to the right direction, when heat intake goes up, heat production goes down. At the top here we have a change in body temperature from the beginning to the end of the session, and there's no change at all. The next, we have exactly the same thing. It's not written here. This is reward intensity. Okay? So when you increase reward intensity, in this case, you increase heat intake. When heat intake increases, heat production decreases. The body temperature is the same. We have another one. When you change force, you're gonna go quickly on this because they're always the same. Just, of course, the values, the exact values change, but what I want to show, this trade-off is always present. So again, here, when you increase the force that you to depress the lever, you have a decrease in heat intake. When you have a decrease in heat intake, you have an increase in heat production. Body temperature remains constant. Now again, we're going to change the force again, but in different temperatures. Okay, the last figure with the force was at 3 degrees Celsius. Okay, so let's take only heat intake. Okay, was something like this. When you increase force, heat intake goes down. Okay, and heat production goes up. Always this trade-off. Well, now you could say when you increase the force, it's obvious that heat intake will go down because the animal can press more. It's too hard to press. The muscles will not do it. Okay, so there's nothing to do with motivation or anything, any interesting physiological process. It's just force. I can press the bar. That's it. Well, if this is true, when you put it -7, you should have the same thing. But now, you see it goes up, the whole thing goes up. And this means the animal was able to press more, because see this reduction from here to here, if we say it is due to the muscle limit, why now, when I put a -7, he can do this? Okay, so it was something motivational. It was not only just a simple muscular incapability or something like that. So you have this trade-off, as it was shown for all the rest, all the others. And this trade-off in general is you don't have to go to the limit to have the trade-off. The animal just don't go to the autonomic response just when he can't anyway have a behavior response, even when the behavior response is possible.